Hello, everyone. Glad to be here. Let me introduce myself. My name is David Flynn, and I am the CEO and founder here at Hammerspace. You may know me from previously at Fusion I/O with the introduction of the modern high-performance SSD and NVMe. But I am here very excited to tell you about lessons learned from working with Meta's team in the Llama2 and Llama3 training environments, things that we have gleaned from that experience and what it means for the use of data. So let's jump in. First, I'll give you kind of a understanding of what we are as a company. You may have heard of Hammerspace before out of the context of the company. We didn't actually make up that name. It is a fan fiction description of the extra dimensional space that things come from when they're pulled out of nowhere. So when a magician pulls a rabbit out of a hat and you ask, well, where did that come from? That was Hammerspace. The reason it got that name is because it was the cartoons where the characters would pull a big hammer out of nowhere to whack the other character with, and it got to be the joke. Where did that come from? It's Hammerspace, the place for those weapons. Or think of it like your first-person shooter game and your RPG. Where do you carry all those huge weapons? It's in an alternate dimension, a Hammerspace. We use that term because it really does personify exactly what we are doing with data. We're making it possible for data to appear as though out of nowhere, that data is not constrained to the physical world of storage systems. And that's really what our mission is to radically improve how data is used. So instead of accessing data that has been put to rest in storage, instead, data lives in motion across a global data environment, across many different points of storage. Think of it as data is physically distributed and yet logically unified. The way we view that is really doing for data what VMware did on the compute side in abstracting the server from the physical server actually running it. We're abstracting data from the physical storage, storing it, and allow data to transcend the storage that it is in. This is absolutely critical and is kind of our first point here with working in these AI environments, and that's that the scale of data and the GPU arrays is so large that data cannot be confined to a single storage system. It needs to be a parallel and scale out and be distributed across many storage devices and even across entire data centers. It also has the convenience of letting you use the existing storage systems and services that you're used to already using without having to forklift upgrade those. In other words, you don't have to throw out what you already have to get to a world of AI. You can continue to use the existing storage infrastructure. Now, when we ask, how is this made possible? It really goes down to some fundamental architecture, and we try to simplify that. You have, on the left, we see the state of affairs today is that the file system, that's what presents you the data. It's the data presentation layer. That file system is built in to the storage system or service. And that storage system or service possesses all of the data about the data's identity. What the data is a rendering of the storage system because the file system exists within it. And the way we manage data is by copying it between these storage systems, which inherently makes it different data. It forks the very existence of the data when you move it from one system to another, because the presentation layer is inside. you get different data. The what being trapped in where the data is means if you put the data somewhere else, it's now different data. So the fundamental innovation here is to elevate the file system to exist above and across all of the storage and allow the movement of data then to happen from behind the data presentation layer. And this allows you to have a singular presentation of data, a single pane of glass, a single namespace, even while the data underneath might move from system to system. So basically, we've pulled the what out from amongst where the data is, and that allows the data to move without changing what the data fundamentally is. This is a inversion of the current architecture, which is frankly upside down. The metadata shouldn't be in the infrastructure. By pulling it out, it allows us to have platform now finally transcend infrastructure. But let's get another double click in here to describe in a little more detail. Today, data is localized, and its very identity, what the data is presented from the storage. So storage that is in NAS system 1, here depicted on the bottom left, different than the data inside of the high performance file tier or in your tape tier or in other data centers. This is, of course, what we know today as data being, quote, siloed. And it leads to all of these pathologies that we see with it being a challenge to move data around. And the way I like to think about it is, in the past, we have been able to take the shortcut of having a one-to-one relationship where an application puts its data onto a storage system, and another application can put its data onto another storage system. Now, it might share the same storage system, it might not, but that's completely coincidental. The fact of the matter is, it's app to data to storage, to data to app, a very one-to-one relationship. And now with AI workflows, that one-to-one has become a many-to-many, because not only does the data originate in applications that are different from where you're doing your AI training, modeling, and inference. So now you have the origin application and the alternate use inside of these AI systems. But the AI systems themselves may live in alternate data centers, and they themselves are often physically distributed. So we end up going from a classical world that was already rickety enough of having applications, data assigned to specific storage, to where now we need all of your different applications' data available to potentially multiple GPU clusters for inference, in addition to the application where it is originating. So we can no longer limp along with the direct mapping relationship of application data to the storage. And this lacks the kind of agility that we need, the kind of cross-access, cross-system, cross-site, cross-application access to data. So what Hammerspace does is actually really elegantly simple in principle. It's to allow all of the data from these different storage systems to first appear as if it were in a single namespace. And this is by pulling the metadata out, the data about the data, the identity of the data. What the data is now outside of the storage where the data is. And this allows you to replicate that metadata everywhere. And so you can give the appearance of having everything everywhere, but that's only by virtue of having replicated the metadata outside of the storage and across all of your different sites. What's left on the storage is really just the contents of those files. But the actual file names, the directory structure, the access controls, the file system, as it were, is now something that exists independent of any of the storage and yet can map and manage the data across all of it. So this is, really important to understand that Hammerspace takes traditional storage interfaces, like I've depicted here, regular old NFS v3, S3, even block storage by virtue of being able to put, say, a Linux white box server on it. But Hammerspace consumes storage interfaces, and we export those self-same storage interfaces. This is not unlike VMware. VMware sat on top of a server and took a server actual hardware interface in and presented a virtual hardware interface out. So server interfaces in, server interfaces out. Hammerspace takes storage interfaces in and all of those self-same storage interfaces out. And it's really important to recognize that a data orchestrator isn't storage any more than VMware a server. VMware wasn't a server company. They abstracted the virtual server from physical servers. Data orchestration and Hammerspace is not a storage company. We are a data orchestration company that happens to be able to take storage interfaces in and storage interfaces out. And let me stop here and say also that the ability to serve object interfaces and NFS v3 and v4.2, so parallel NFS and regular NFS, and Windows SMB, all of this from the same namespace is incredibly powerful. That's why the way to think of this is a data platform. We are not just a POSIX shared file system with NFS and SMB access, but we're also an object storage interface as well. That doesn't make us an object storage company any more than it makes us a NAS company. Again, we are at the data orchestration layer. All right, so once you have the ability to overlay this data abstraction layer, it actually accelerates the access to data because now clients can access multiple storage systems in parallel, because at the heart of Hammerspace is the parallel file system architecture in the NFS protocol. Parallel NFS makes the heart of this. So if you're wondering, why is this possible now? Why wasn't this done before? It's because parallel NFS, while attempted, had never been delivered. Hammerspace was able to execute on that, and using that parallel NFS, make it possible to route data in mass parallel concurrent to many different storage systems. And this is why actually adding the abstraction layer increases performance. Imagine a world where plugging in VMware actually made your guest operating system run faster. That didn't happen because VMware was a layer that had a performance tax to it. And yet it was still incredibly valuable, so much so that we accepted that any one guest might run a little bit slower, but that would let you pack a bunch more on there, get better utilization, even though peak performance of any one might have been lower. And yet we did that. Well, what I'm proposing to you here is that the introduction of the data abstraction layer, abstracting file and object from the file and object storage, storing it, actually has the nice side effect of it actually accelerates the access by making it parallel and concurrent and moving the metadata closer so that you're not having to go all the way back to the storage to get to the metadata. So it speeds up metadata intensive workloads and it speeds up data intensive workloads, IOPS bandwidth in all cases. So really powerful concept that you can add the missing virtualization layer for data and actually have it accelerate the access through to data. And now you see why this architecture fundamentally is so important for the AI and ML workloads, these training workloads like with Llama2, Llama3 from Meta. And this was the principal reason why Meta selected Hammerspace, is because it was standards-based. It could use standard Linux storage servers, which they have in the thousands, and can create a high-performance parallel file environment on it. We're going to go into another double click on that actual architecture, because if you're at all a technologist, you'll understand that's a pretty bold claim to say you can add the abstraction layer and have it actually speed things up. We're going to show you how and why that actually works. But the proof is in the pudding, and that's just looking at the companies that are using Hammerspace today for this. It kind of proves that out. Now, once the data is in, it allows the metadata is separated. Data can move freely across the environment without being different data. It's the same data, not because we've separated the what from the storage where it exists. You can change the storage, and the what stays the same. So data can move across any of it. So really simple concept: storage interfaces in, storage interfaces out, and the ability to, at the swipe of a mouse, control where the data is realized on the infrastructure. And it's not just one place, but data can be realized in duplicate, in triplicate, in many different data centers on many different storage systems or storage servers. That exact same file might exist in many places, but it is now still just one file because the metadata is singular. Even then, the metadata is replicated, but it is maintained synchronous, or it's maintained consistent across all of those sites. Eventually consistent, I might add, because to do it strictly synchronous would cross-couple the sites from a performance perspective and slow things down, and from a reliability perspective and compromise reliability. So the way it works across sites is actually eventually consistent and loosely coupled. So this is the general principle. And what it means is you can access your data as if out of thin air, because now the storage is interchangeable. The closest analogy I've been able to come up with on this, and I think it's a very correct one, is with your personal data on your cell phone. Since the advent of the smartphone, and the fact that we had to replace them rather quickly. I mean, laptops, you remember having to migrate your home directory from one laptop to another back in the day? That was prehistoric. If you were to ask me to find files, I probably have them because I have my home directory that I copied over onto my new laptop. And then when I migrated from that one, I copied that into my next home directory. And then I copied that into my next. I have literally a nested set of my old home directories that are like the Russian Matryoshka dolls, those nesting dolls. And I could probably find the work material from back then, but literally I would have to go like an archaeologist hunting, chipping the rocks to try to find where it is. Ever since the advent of the smartphone, probably because the replacement cycle got to the point of absurdity and having people manually migrate was going to be crazy. So we came up with data orchestration. The iOS platform and the Android platforms, whenever you replace your device, your data is just exactly where you left it because it now lives in a logical place, not a place that's physically bound to the hardware. So we're doing that same thing. We're giving data a logical existence that is independent of the physical storage so that it can stay the same logical data over time, even though the storage may come and go. And the incredibly counterintuitive thing here is two things. Number one, it makes data actually more permanent, because in a world where you have to manually copy things and where it inherently is a different place whenever you move it, it's very easy to misplace it. And so in a world of store and copy, it's harder to keep a hold of the thing through time. In a world of orchestration, it is moved for you automatically, preventing human error, and it stays in the same logical place, even while the physical underneath changes. So the very powerful thing is that data orchestration, having data live in motion, actually makes it more permanent than the very storage system storing it and the process of store and copy. And the other thing is, you might think by adding an abstraction layer, we're actually making data more abstract. But in reality, separating the logical data from the physical storage allows you to have a more concrete understanding of your data, because you don't have all of these copies that fracture your ability to identify with what is the data and where is it. So the other counterintuitive thing is that adding in this abstraction layer allows data to become a more real and more concrete thing, because it now exists in the same logical place consistently over time. Let me point out that this technology that we have built into the NFS protocol and into Linux, based on parallel NFS with many enhancements, is so complete. It allows data to move while it's being accessed. It can actually pick up an individual file that's being generated or being interacted with reads and writes, and that file can be moved from one system to another without even a barrier or a flush interrupting the IO stream. So very, very powerful. Think of it like storage vMotion that allows you to move a VMDK file underneath a running VM. Well, here, underneath any running application, we can still pick up the files and move them wherever they need to go, even while they're being interacted with, even while there's ongoing IO. So this is revolutionary to have, storage vMotion in at the file system level and data able to move freely anywhere, whether that's back into object storage or even tape systems, or forward into high performance flash, or maybe even all the way into the compute tier, with tier 0 being co-located on the compute nodes on NVMe flash. All of that now exists as just a distributed data environment. Okay, so that's the general concept. Now let's get a little more specifics. This is not just a high-performance parallel file system and data orchestration. It is also a very robust and complete enterprise NAS. It has all of your data services that you would expect, like snapshots and clones and deduplication, compression, even things like file versioning and undelete. But other things like audit and antivirus and worm, all of the things that you have come to expect from an enterprise-grade NAS, this now does. And at the orchestration layer, the individual storage systems don't need those features. Those capabilities are all added at the orchestration layer. So now you have the ability for data to move freely across any storage, tiered up, tiered down, spread across, multiply instantiated. You have all of the rich data services, and then at the heart of it is this parallel file system that allows you to have accelerated parallel concurrent access without being in the data path, by the way, because the client is now built into Linux and it knows how to follow the routing. We'll talk a little more detail on that in a minute. And then it presents all of the expected protocols, like the file protocols, NFS and SMB, the object protocol, S3, as well as, interestingly enough, in a container environment, we support CSI. And in that case, not just shared file, but also block and local file volumes in container environments. So Hammerspace can be the one-stop shop for all of your persistent volumes of any type. Block file and object persistent volumes can all be supplied through the same CSI. And by the way, on top of any of your existing storage. So you don't need to have vendor-specific CSI With Hammerspace as the abstraction layer, you can use any storage and get file, block, and object container volumes from that. All right, so very complete and robust feature set there. But exactly how is it deployed? And let's go into that. So Hammerspace is software. It runs on servers, whether those are virtual, physical, or cloud instances, doesn't matter. That software comes in two forms. One is the metadata service we call Anvil, and the other is potentially data services, the data movers, the stuff to source block storage, the things to move things around object storage and do the compression and dedupe. So those are simply software appliances that run on bare metal VMs or containers or cloud instances. Once you install and run that Hammerspace machinery, you simply point it to your existing storage, whether that's block storage or file storage or object storage. You point it to those existing data sources, and you can assimilate the existing data sets simply by pointing us to an existing file store with potentially petabytes of data and billions of files. Hammerspace can immediately serve client access through to it. In other words, there is no downtime. With merely unmounting and remounting through Hammerspace, you can have access to that existing data. And once you've assimilated the data, so there is no data migration even to get it into the virtualized Hammerspace environment. Once it's there, now with the swipe of a mouse, you can move the data around. You can decommission storage. You can add in new storage. You can have it redistribute the data to better performance balance it, load balance it, to better capacity balance it. At that point, you are providing fast parallel access to data, and the data is able to seamlessly and transparently move. And then finally, you can do this in multiple data centers. Install the Hammerspace machinery, source the existing storage and data sets within that storage, and with Hammerspace, you can then share those file systems to other data centers. You can even assimilate data into the same shared file system from those different data centers. And so now you can create a seamless global data environment where all of the data exists behind a single pane of glass, regardless of what silo it originated from. So let's move on from here. Let's get into the double click on the details, because I'm sure that's really, everybody's like, well and good, okay, great. Like I said, if you're a technologist and versed in the field, these are really bold claims. So let me just restate here. In the world of unstructured file object data, you've had the NAS world, which tends to be designed around being really safe, a good caretaker of the data, even protecting it from user error with things like snapshots and clones and all of the fancy data services, and really easy to use. It's plug and play, it uses existing protocols, but it's not known for being particularly scalable and fast, and it's not particularly low cost. Now, in contrast, HPC file systems, they err on the side of being super, super fast and software defined, generally easy to overlay on existing infrastructure and to get really good scale. So they're made to be affordable at scale, but they don't have all the fancy data services and stuff to help you protect the data. And they are often like a Formula One race car, something that is prone to break down, not necessarily easy to own and maintain. So they take kind of opposite design points, which makes sense. Why have those two camps endured to this day? And you still have new companies that are introducing newer forms of NAS, more flash and maybe a little bit faster. And you have other companies that are introducing new HPC class file systems, maybe trying to be somewhat easier to use and deploy. But the truth of the matter is, the reason why there exists such a chasm between these two worlds is because of the client, the technology, the protocol. Think of it like a highway system versus traditional roads, and whether they are public roads that are open for any vehicle's use, or whether they are proprietary roads that only special vehicles can travel on. Because the world of enterprise NAS uses public roads, but to date, the only roads available have been surface streets with potholes and stoplights and stop signs and traffic. Not that great at conducting very high throughput, but they are a public right-of-way. They are built in. Every operating system on the planet has either NFS or SMB or both, and so very easy to plug in to this road system. Now, the HPC file system guys said, look, those roads are too slow. We've got to build a custom highway system, but that has to be laid down in every single machine that's going to be interacting with the data. To plug into this highway system has to have custom modules, has to have custom protocols. That's why it's a pain in the ass. And so you've had these two camps because of the lack of having parallel file system architecture, a highway system architecture that is a public right-of-way, something that's built in and standards-based. That is, by the way, what parallel NFS is. And I will also call out here that object storage, not coincidentally, takes a 90-degree different approach than either of the other two. It's made to be very, very good at long-term safe retention of data and very, very good at being cheap and very deep. But it's not particularly easy to use. You have to use REST interfaces from user space. Heck, your operating system can't even load its binaries. It can't even load programs from it. You can't point your OS to it and say, hey, run this application. It can't even store your application binaries and libraries because the OS doesn't even know natively how to communicate to data that's in it, meaning you have to have a user space REST interface to the thing. And it doesn't have the rich ACLs and other support, so it's rather rudimentary when it comes to interacting with multiple users and groups of users and so forth. After all, it was called S3 for a reason, super simple storage. And it's partly because it was so hard to build a scalable file system that they had to take a different design point, and the design point is very cheap, very deep, and very safe long-term retention, but doesn't even have random read and write capabilities. It's not particularly performant. You can get decent throughput, forget latency, forget IOPS, that sort of thing. Well, what we're here to say is that thanks to the parallel NFS protocol, we are able now to deliver something that excels on every single one of these dimensions because it bridges that void. It is a public use superhighway system, and it allows one to build ultra high performing vehicles that still can be very convenient and easy to use and very robust. So the net result of this is that that parallel file system architecture allows you to get linear scalable performance into thousands and thousands of nodes. You double the number of nodes, you get double the throughput because the switching is, the switching is the only choke point. There's not any controller nodes. Let me go into more detail here with the architecture. So if we take this chart here, you can see on the far left, traditional NAS architecture, you have storage nodes and controller nodes. VAST calls them D nodes and C nodes. The controller node is what adds the file system. The data node is what holds the storage. And while you can co-locate those two functions on the same physical hardware, the data still has to go out over the network to peers and back in. So even if the controller and storage functions are combined, the data path nonetheless is still this exhaustive. And what I've depicted here in these red arrows is how many times the data must be transmitted over a bus or over a network, chip to chip or over a cable. Coming from NVMe through the host complex, out the network adapter, through the switching, back in the NIC, the CPU, back out the NIC, over the front end network, your NAS network, and into the client. And you can see from the far left, if you traditionally, it would take no less than 10 times that the data has to be transmitted chip to chip or over a network. Now, if you support GPU Direct, which Dell and NetApp do, and at least Cumulo hadn't for a while, I don't know, they may by now, it allows us to reduce that to 9. Notice the difference in the client. The data goes directly from the NIC to the GPU. So GPU Direct and all of the hubbub saves 1 out of 10 data retransmissions on a NAS system. That's why people don't generally use NAS to feed GPUs, because there are so many data hops just to get there that it dwarfs even what GPU Direct does to help the data go more direct. So VAST recognized that you could use NVMe over fabrics, and notice at the bottom, that allows data to go from NVMe directly out the NIC without having to go through the root complex, without having to go through the CPU. So now the bottom box, it only takes 1 hop to get out the network as opposed to 2 to get through the CPU and then out the network. So we go from 9 to 8 times that the data gets retransmitted. This is the major advantage that VAST has over other traditional NAS vendors, is that the data only has to be retransmitted 8 times instead of 9 or 10. Now, parallel file system architecture and parallel NFS allows us to go from 10 to 5, because now data doesn't need to go through a controller. The metadata service is a sideband control plane, and the client is smart enough to know how to do a DNS-like look-aside lookup and get the routing information so that it can make direct connections to the storage nodes. In other words, this takes the controller node out of the data path and allows the data path to be even more direct. And that allows us to get much higher performance. Now, take that a step further, and you could embed Linux into the SSD and have the SSD originate data on the network, as opposed to needing to sit inside of a storage server at all. And we're working with the SSD manufacturers on this. And this will redefine the capacity tier, allowing you to have very, very cheap capacity by getting rid of the storage server chassis entirely. And then tier 0 allows us to use the NVMe in the compute tier as the storage. And when the client goes to open a file that happens to be housed on that same physical host, then the data gets accessed directly, just like with local NVMe. And the enhancements to do this have been upstreamed into Linux in the last merge window, in the 6.12 merge window. It's actually 2 merge windows ago. And that's the local IO patches that you can go and read about. Makes for incredibly higher performance. Now, it's not an either or with these 3 architectures on the left. You can have dedicated storage servers. You could have Linux Ethernet native SSDs, and you can have tier 0 all in the same environment and have data exist distributed across all of those based on policy existing where it needs to exist to get the right level of performance. So this allows us to get crazy levels of performance. And so when we take a look at Meta, they have traditional storage servers with a bunch of NVMe. That's the bottom right here. Thousands of those storage servers. And with Hammerspace anvils, as the metadata control plane on the side. Only 3 of those were needed for, say, 1,000 storage servers and doing tens, in this case, 40 some odd petabytes of capacity and feeding tens of thousands of GPUs. Very powerful architecture because it allows us to aggregate and orchestrate data across thousands of commodity off-the-shelf Linux servers with no software other than just Linux required, and feed that into thousands, or in this case, tens of thousands of GPUs, again, with nothing but virgin off-the-shelf Linux. So Hammerspace is very unique in that we are the only parallel file system on the planet that can use native Linux as a client. But not only native Linux as the client, we can use native Linux as the storage server as well. So it's 2 very unique things that means the entire data path from client to storage server is just virgin unadulterated Linux. That is a very compelling reason to adopt Hammerspace versus another parallel file system. Aside from the other benefits of actually being truly enterprise-grade NAS with all the rich feature set and highly reliable. Reliability was one of the other major reasons for Meta's selection of Hammerspace. They were able to show that you could lose hundreds of storage nodes and the data would still be available within seconds. And it would self-heal within tens of minutes, having resilvered everything across the storage. This was incredibly important to them because they wanted to be able to continue to run their AI environment the same way they run the website. And the website is designed to be very resilient to outages, whole power feeds going out, whole rows of racks going out, and yet the website stays up. So it was made to be sort of a loosely federated and highly redundant environment. And Hammerspace fit that bill very nicely with the reliability. This Pure Magic quote is actually talking about using data assimilation. They use that to move from an old data center to a new data center. And even though the data took 3 weeks to copy, and even just scanning the metadata took on the order of a day, nevertheless, their AI teams were not down for more than a mere 3 minutes, just the time it took to remount through Hammerspace, because the metadata scanning and the data moving happened subsequently in the background while they were already using it. And any particular directory, it would pull that metadata for. And any particular file, it would go and fetch the data for it. So it might have been slightly higher latency the first time you cd'd into the directory or the first time you access the file, but it was so fast, they really didn't even notice. And then over a period of the day it took to fetch all the metadata, and then the weeks that it took to move the data, ultimately everything was relocated and they could decommission the original site. So very, very powerful that there's zero downtime for migrating data, even across data centers. So if we take a look here, the architecture on multi-data center is, we have depicting 2 data centers here. We do have some customers like Epic Games that has a dozen different data centers. Again, eventually consistent, loosely federated, allows you to have massive numbers of sites and have it very robust. You have the Hammerspace machinery, the Anvil and potentially the data service nodes running in each data center. And that allows each data center to be local access. Your metadata is local, and the data can be moved and stored local. So every data center gets the performance of local access, but it's to a shared file system. You write a file over here, it's readable over there, you change it over there, and it's readable at a third site. It doesn't matter where the change originates, the system recognizes that because that's all synchronized in the metadata. So very, very powerful concept. So let me jump back a few slides to one that we skipped. So this kind of puts a summary on it. We already talked about this first set, but Hammerspace and hyperscale NAS includes the ability to assimilate existing data sets by reference, to move data freely across systems and across sites through service level objectives, through the swipe of a mouse and a declarative intent language, and then unifies that into a single namespace, a single global namespace across those sites, and up to dozens of sites. And it does this with enriched metadata and with the advanced data services. So truly unique. And it is in aggregate, all of these capabilities that make Hammerspace really excellent as a data platform for AI training. So kind of to summarize here, jump back to where we were. Yeah, this is it. So this is needed now because AI and GPU computing workloads are forcing the industry to grapple with the long-standing intractable problems, converging HPC class performance with enterprise NAS reliability and robust feature set. That is the first long-standing intractable problem that the industry has failed to deliver on until Hammerspace. The second one is the ability to eliminate data migrations. Through data assimilation, we can incorporate existing data. There is no need for swing boxes, for downtime. It's a simple remount. And then data orchestration, moving data across systems and across whole data centers. And then number 4, one of the biggest of the long-standing intractable problems is how to have the same file system with local access performance from many different data centers at the same time. How do we have a single global namespace across data centers? And then how to incorporate local NVMe with the performance of local access into a shared file system. Tier 0, another key intractable problem. It's actually one of the reasons why I used this architecture in the first place. Having invented what became NVMe, I desired a file system that can incorporate server local NVMe and give you the exact same local access performance when the data happens to be orchestrated to be co-resident. And so Tier 0 is actually the realization of the original founding desire of using a parallel file system to be able to move data into the compute tier. Now, if you ask, why is this happening now? Well, number one, the demand driver. Before, there wasn't need for this kind of crazy performance or the agility of data across systems and across sites. AI really is the forcing function to force us to grapple with those demons and to finally fix these long-standing intractable problems. But the key thing that we have in our camp for being able to do this is that Linux has consolidated the OS landscape. So at least when it comes to performance and scale, Linux is it. Now we also support the traditional NFS v3 and SMB and S3, all these other protocols. So we support any client you want, but the parallel NFS is built into Linux. And that's where it needs to be, because that's where, if you're worried about performance, you're running native Linux. That's where the GPUs are. So Linux consolidating the fractured OS landscape really is the key enabler for us to finally tackle some of these long-standing intractable problems from the world of data and storage. And lastly, Hammerspace has been able to address this. We've been very uniquely positioned because our CTO is the kernel maintainer of the NFS stack. And like I say, because of my background as a technologist and having been a party to the solid state revolution and in high performance computing and those types of systems, that financial success has also allowed us to really tackle these things. And we got started early. I mean, Hammerspace, this project, I started on like 10 years ago. So skating to where the puck would be. Actually, it took longer than I expected, both for the tech to be built and delivered, but also for the industry to, for the use case, for the demand driver to arrive. And AI, ML has really only been in the last 24 months. Seems longer, but that's really just because of how fast the industry moves. So infin here, the key innovations are the extreme performance of a parallel file system with the convenience of being NAS, built-in protocols, plug and play, very robust, easy to use, rich feature set. Number two, the ability to incorporate existing data with a mere reference to it, incorporating data by pointer. This we call assimilation. No downtime, no move, no need to copy data, no need to even wait for it to be scanned. And then once the data is in, the ability to move data through intent-based objectives, a declarative model, and have data move and be realized on the infrastructure according to the stated intent, even across whole data centers, across diverse types of storage, across distributed and parallel systems. And then the ability to serve that as a single global file system with read-write access everywhere, with eventual consistency and collision resolution. All of this with enhanced metadata that allows you to build programmable metadata workflows, and with incredibly powerful data services, not just snapshots and clones, but also full and granular file versioning, as well as undelete capabilities, offloaded recursive deletes, even the ability to clone entire directory structures with billions of files instantly. We use that same assimilation technology to offload and lazily realize a recursive clone of an entire subtree. So you can clone entire data sets instantly and immediately start modifying the copy without affecting the original. These data services are very powerful, and they were made possible by the fact that the file system is working in metadata and doesn't have to, wade through petabytes and petabytes of data at the same time. Separating metadata from data is really the key to all of these things being deliverable, and that's at the heart of the parallel NFS architecture. So with that, I'd like to, thank you for your time, and hopefully my monologue wasn't too boring here and going through all of the architecture here. But these are some of the things that we have learned are of incredible value in the AI and ML workflow world. Is starts with just having HPC class performance and scale, ability to incorporate data sets, to be able to move data sets, be able to render them in multiple data centers, and then use powerful metadata workflows and data services to control that whole thing. So with that, I'll turn the time back over to our panel. All right.